I have 3 more slides to show you ZIKA. So when you have this ZIKA, again, ZIKA is an own virus. Because of microcephaly, and you have so many proteins, 10 proteins, 1 poly genome, and then you include the polyprotein and process into different kinds of proteins. One of the proteins is E. It's called own protein. It's a receptor for the receptor binding and entry. So as I also mentioned, and when Malik sitting here did his PhD with James Porterfield. I did my PhD in flavivirus with Ernie Gould. That's a coincidence that also Malik is here today. So antibody-dependent enhancement is a common phenomenon for all the flaviviruses. So now I realize, we have so many neutralizing antibodies or monoclonal antibodies around. So the first work we have done. So this is the E protein. We solved this E protein as a typical dimer. It's known for a long time, nothing new, nothing normal. It's a typical flavivirus structure. But what we have done, as you know, so this is the structure, and there's a loop, domain 2, fusel loop hiding here, fusel loop hiding here. The fusel loop covered by domain 3, that's also impossible. Fusel loop is responsible for the binding for the cell membrane. So some antibody existing, we know already, this is the antibody. So one of the antibodies we call it 2A. 2A antibody can bind the fusel loop to stop the virus entry. So it's a typical neutralizing antibody. So then we saw this is the first fusel loop, intact fusel loop covering antibody structure. So we've solved this structure, clearly shows, this is the antibody, and this is how they interact, especially when you are talking about tryptophan 101. So from the mutagenesis, virologists did a lot of mutagenesis, shows fusel loop tryptophan 101 is very important. But we confirm this antibody covers. There's tons of fusion loop targeting antibody. We confirm this one, and they bind very well. So far, for all this, we have 3 antibody complex with the E so this is the dengue from Gavin Squitty and Felix Ray's group. So they targeting this loop as a very good neutralizing antibody. And we got, this is the antibody, they bind the fusel loop. Another one is for West Nile virus. West Nile virus, another protein called E53. They touch the fusel loop, but not like the 2A. 2A totally covers the fusel loop. So now I want to get a conclusion. So because we have so many viruses, and for dengue and Zika, we need to define why we have some antibody-dependent enhancement. So the current theory, FC part of the antibody plays a very important role, but that theory cannot explain everything. So this is why, in my opinion, we need some more monoclonal antibodies in complex with all these E protein to see maybe there's some other mechanism. For example, this 2A antibody can neutralize Zika, but it's less efficient. For the yellow fever, for dengue, this antibody is a broadly neutralizing antibody for flavivirus. However, and for the Zika neutralization is 100 times less than to dengue. Why is that? And also, our initial data, we need to go further. Only when you have the low concentration of the antibody, you might get the ADE, antibody-dependent enhancement. In this case, 2A, when you do the homogenization, when you do the high concentration of the 2A, for the Zika, you see ADE. Why is that? So anyway, I leave this question. I want to really encourage a lot of people, because now Zika dengue it's a serious problem. Encourage all of you to try identify human or animal, even monkey or mouse antibody. I like to collaborate with you and a molecular antibody to try to define. That's a very important scientific question for flavivirus antibody-dependent enhancement. Okay, I will stop here. Thank you very much. Thank you for your time.